on growth and decay. Hope you're all sitting down taking notes. This will just be a broad overview, and we'll go through many more examples in class. Now, exponential growth and decay famously we use for growth, population growth, particularly bacteria in the early stages. So population growth early on, you can imagine starting with a very little amount. The very little amount of bacteria doubles, quadruples, octuples, grows a very little amount at first, but then as each cell subdivides further and further, you get very rapid growth. Similarly, compound interest, we'll look at how this actually works, but if you have $1 million in the bank account, the first year it might earn $50,000 interest, but then the next year, that million and the $50,000 in there all earn interest together, and the next year you get more than $50,000, and if you're lucky enough to have $1 million or anything close to it, over time it grows up like that also. So, exponential graphs are for modeling growth that is slow at first, then rapid. So for example, if you put, say, 24 rabbits into Australia with no rabbits, which we actually did, that was a terrible idea, put 24 rabbits into Australia, you can imagine that after a year, well, they'll have bred a bit and there might be 80. But then after another year, so starting off at 24, at times 0, after a year there will be 80. But then it really starts to accelerate. What was that? 400 the next year? And yeah, somewhere around now, 100 million? I'm not sure. But population growth grows extremely fast. Now some of you will say, and quite rightly, that at some point it will stop going up like that. Even rabbits will run out of grass and it will start plateauing off. That function is called a logistic function. It's a very cool function. Either Google it or wait till you're 11. But generally, we'll only consider this early stage of very rapid growth. Now, we could also consider modeling the spread of a rumour. Say, when you whisper it to one person, then both of you whisper it to two more, and then everyone who knows whispers it to two more, and so on. It keeps doubling every hour the rumour grows. You could also model like this. So lots of things where growth happens rapidly initially, we can model using exponential functions. Similarly, where decay, so decay is where decrease happens rapidly at the start. Now decay most famously happens, most mathematically true, the most commonly used case rather, is when we do radioactive decay. So radioactive decay, if there are 1 billion atoms, a set number will decay and it will look like that. Alright, now the form of this function, the general form, takes this form here, where y is clearly the y-axis, t is what's plotted on the x-axis. The reason we use t is because that usually symbolizes time, doesn't have to. And then we're going to look at k and a and what they do. And to do this, we're going to look at the graphs page. Hello, Desmos. Now, look on the left-hand side where my cursor is on this slider. K is 2.3, A is 1.5. I might just make a 2 for now. 2.1 will do. Now watch what happens when K changes. When K is positive, negative. Alright, it's buffering and having trouble keeping up. I'll pause it somewhere. 7.3. What you might notice is that the y-intercept is exactly 7.3, 7.34, and the slope is in a positive direction. So increasing rapidly. So if, for example, we wanted to start with 10 rabbits, k would equal 10. The reason is because when x is 0, so a to the power of 0, whatever a is, a to the power of 0 is 1, so that means the y-intercept will be k, because that's k times 1. If it's negative, same thing. But note, there is always this asymptote here, this called horizontal asymptote, where the graph reduces to the line y equals 0. Alright, so let's leave k at 4 for now, or 3, and change a. When a is positive, the more positive is, the steeper the graph, as it goes, the really interesting happens between 1 and 0. So at 1 it's flat. Less than 1, we look at decay. So between 1 and 0, we reduce sharply, and we'll look at this more in class. Right now the important thing is just to get notes down of what happens to K and A, and then as K goes negative, that's A. As A goes negative, not a lot happens because you can't raise. Ooh. Zero and gone. Where is it? Actually, it doesn't matter. We never really consider the case where A is negative. A is always between 0 and up. Alright, don't want to take too much of your time, so I will just show you this, and yes, it's cut straight from the textbook. Please have that down in your notes. If you want to, you're welcome to print that out and just stick it in your notes. The important thing to remember is when A is greater than 1, exponential growth occurs. When A is between 0 and 1, decay occurs. Now, growth rate and decay rate occur like this, changing A. When A is growing, you would do 1 plus the growth rate. So if you are growing by 4% a year, like my bank account hopefully is 1 plus 4 and 100. That would indicate a growth of 4%. Note that simplifies to 1.04, and if you get quick at this, you'll start writing the percentages like that. If my mortgage decreases by 3% a year, it'll be 1 take 3 on 100, or 0.97 that we multiply, giving this function the basic form. Please have that down. We'll continue this tomorrow in class.